Hello, everybody. I suppose I'll stick to English. Welcome. I'm from the company Mesosphere, but I'm not going to emphasize that as we go forward because I know this is all about open source, and I want to show you how you can make your data center run with open source only, of course. And then we can extrapolate from there after the talk maybe, but not in the talk. What's this all about in one sentence? Well, this is the title. So why would we need an operating system? Well, other people before us have figured this out. Large company running very large clusters has more than a decade of experience in what I'm going to talk about. And what we want to enable is that not just them, but everybody else who has the means and time and effort put in can also run at very large scale. There has been a lot of beneficial side effects of the development that Google has been undertaking in tech transferring some of the things that they came up with and that they've leveraged to get their enterprise running back into the open source pool, and other people have picked it up and grown these efforts. For example, MapReduce got molded into Hadoop and has grown tremendously since. There has been Bigtable, which became non-SQL databases, so for example, MongoDB. Now, you can't always draw a direct line, but there is some connection there. C groups were donated to the open source and are now a really important ingredient in what I'm going to talk about. And then eventually there was this really influential book, The Datacenter as a Computer, which is the general idea here. And our chief architect and a few folks around him in UC Berkeley formed the Mesos operating system, distributed system operating system kernel, you could say, in the context I'm getting to, around that time. And the history is that Ben then joined Twitter, and then they adopted this for running their clusters with it, and they have since 2010 been pretty successful running on Mesos. So that's going to be the focus of our talk. And since then, well, there have been many more frameworks than just what Twitter runs on Mesos, and that will also be a topic. But let's step back. There are two things I need to talk about here. One is data center, the other is OS, and then how they're connected and how we're going to make it work. So let's start at the end with OS. What happened with OSs, and where did we come from? Where do we want to go? And how does this new way of doing things relate to older efforts? Where did we do a 90-degree turn here? That's what I want to get at. So single system OSs for these things here and these things, they went through a lot of developmental stages that have been greatly beneficial to where we're at now. So we went from single something to multi-something. I don't need to reiterate that. Many of you have lived through this. Some of them have definitely some recollection of that. We have more bits, more bandwidth, more storage, more everything. And then a really important step was virtualization. But virtualization initially came for all the wrong reasons. You wanted to have your Windows software resurrected quicker when it crashed, things like that, or you wanted it to be isolated. You didn't really think about large cluster computing when you first used virtualization, I bet, right? And then you wanted also a more lightweight way to do it eventually, because it costs a lot of time and effort to bring up a virtual machine or an image and then reuse it. Once you have one, okay, you can copy a few gigabytes and you're happy maybe. But it would be better if it became spiffier. So along came containers, and they let you package things in a much more smaller format. And today we have Docker as the predominant format, maybe the most widespreadness, and a lot of Docker fans in the room maybe. Raise your hand. Yay. Rocket. Let me containerize this for you. All of the above. Yep. And well, we've gone full circle, and this for me is the irony. We started out with static libraries because we didn't know any better. And then around the early 90s or something, the whole craze, or a little earlier, was, oh, let's build dynamic libraries. So we can save some space and reuse stuff. And then configuration became hell, because once you wanted to reduce a dynamic library, it might depend on another one because it's not baked into the application. Applications downstream might fail, and so on and so forth. So, but if you use static libraries, you would run out of disk space or memory space or something. Now, with ample space, lots of available resources, you can put stuff into static libraries. Guess what this thing is doing? No dynamic libraries on here, as far as I know, in most apps at least. And containers, you can use dynamic libraries or static libraries, doesn't matter very much. They just get thrown into the container, they sit there and are nicely isolated from somebody else's container that uses completely different versions. And that makes life a lot easier. Okay, so moving on. Next stage, so basic OSs have grown nicely in some ways that we like. Now you have more than one computer, because one computer by itself isn't large enough. So what you do, you put them together, draw some wires, and build some software, and you have a cluster. The first efforts there, I don't know if 80s is doing it justice to my awareness. Maybe it was in the 70s. Maybe someone can beat me to the punch there with the earliest literature, but that's when I became aware of it. People were trying to build cluster operating systems. And by the way, asking me any questions at any time is totally okay. Just interrupt, all right? Okay. And these were aiming at high availability, load balancing, and they were very location transparent. They always tried to provide a single system image. So what you can, and that's why, that's generally a trend in computing, that you want to preserve legacy applications, also run them in a context that has some new quality. That same thing applied here. And these things are still around, but they top out at maybe a few hundred nodes, something like that. Anybody managing one of these still? Maybe, some of you, right? Compared to what we're going to talk about, they provide a more clean interface to the developer maybe, because it looks like a single system, but for the operator they're relatively hard to manage. And so people moved on a little bit. But first they expanded from there. And we went from these smaller clusters to grids that could span continents and all that, mainly in the HPC world. And there are what's known as job schedulers as the kind of the kernel of the activities there. Something that you would give a description and then would run multiple programs on your behalf in a certain pattern with certain responses to the outcomes and so on and so forth. And these schedulers would be using some declarative descriptions of what needs to happen, and would also be reactive to faults and all kinds of self-preserving actions would be in there, but they would still be relatively monolithic. Now, all this was mainly in technical computing, and maybe in the 2000s people became aware, I was working at Sun at the moment, so I noticed that things like Grid Engine came up, or N1 and things like that, way back when. And people also at the same time, a lot in Germany here also, they went to these SOAs, and all these things flowed together, and people made job schedulers a little bit amenable to enterprises. And people want to run clusters in enterprises as well. So we went from grid computing then to grid middleware, and I'm not going to mention Corber because I don't know how it fits in here. And eventually we ended up with cloud stacks. All right, this is my own faked version of history. You with me so far? Okay. And in one aspect of this that I want to emphasize is in the early stages of virtualization, what we had a server, and then we would have virtualization, and that enabled us to run multiple isolated apps there. And the emphasis in virtualization was really on isolation in the beginning. And then later, so we had small apps, and we built bigger and bigger and bigger servers that could run more VMs. And nowadays, we're trying to build big apps, but we make them from small things, and we have lots of them, swarms of them, and we have many, many, many servers, and we don't really care how capable the individual servers are unless we need something special, like there is a lot of data in RAM that we need to hold for a certain task, or we need a certain GPU or something. But absent that, you can chop, 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 chop. And so And then you can commoditize horizontally, and you end up with cloud computing. And then you have all these keywords, SaaS, PaaS, IaaS, and the front runners, historically speaking, were Salesforce and maybe Amazon with AWS that had the first big successes and established this, and then everybody followed. But it wasn't for the lack of trying of others before them. Importantly, there are these different system layers. And the question is, if we built an operating system for the data center, what layer would it be at? Would it be like these original cluster OSs trying to hack the kernel and expand it with distribution capabilities? Or would it be above these OSs? And if so, would it be at one of these three levels? Where would you suspect it would get set up? And meanwhile, we can observe that people have been not only using public cloud, but they've also built their private cloud stacks. And that is maybe informative where this might be heading. And there are some older ones, some newer ones. I suppose a lot of you have probably worked on OpenStack. Maybe someone? Yeah, that seems common. Or CloudStack? Or okay, not so many? What's your preference? Anyone? Okay, so these are the questions that typically come up. So a lot of the industry is kind of sitting at in this area of discussion, I sense. Maybe not everybody in the room here, but I hear that a lot. I use this one, no, I should be using that one, and okay. What's this for anyway? Well, you want to run a data center somehow. What's a data center? Well, I looked up a website that starts with a W, and it says a facility to house computer systems and associated components. It could be networking, storage, cooling, sensors, whatever. So most of the time, a data center doesn't only host one cluster. It may have several. You may have one for your web services, another one for your analytics, another one for testing, another one for development, and so on and so forth. And what I'm trying to convince you of is that at least for production, you don't need so many. And that has certain advantages. So that's what I want to focus on, how we end up with just one production cluster. Well, I personally would still run a test cluster aside from it so that they don't influence each other, because you can never be sure whatever you're using to run your cluster that it has no interference whatsoever. But for the purpose of running your business, one should do the trick, aside from geographic redundancy and all that kind of stuff. So talking about one location. And these clusters that I'm usually concerned with, they're in the tens to tens of thousands of nodes. So it is a large, large range. And I'm going to get to why it should be such a large range. But what we don't want to have is that you have a small little company, you end up buying a few computers, you hook them up to the network, you deploy your app, you grow, and you have 1 million customers, now you need 100 servers. So you move to some other cluster, maybe you go to Rackspace or something, or you go to AWS or GCE, and you migrate there. Then you run up the builds once you reach 500 or 1,000 nodes, and you notice, ooh, that's getting kind of expensive. Maybe I should have my own on-prem solution. And you want to move back, and you buy 1,000 computers, and you put your stuff back there. Guess how long that takes? Any experience values? I mean, yeah, so it costs time, and time is terrible. It's probably worse than money, and it also costs a lot of money to move around. So what can we do to mitigate that? That's also something we're thinking about. And yeah, and if you have several clusters, then they have different requirements how you move them. You're probably using different techniques to set them up, so you also need different techniques to move them, and it all gets very, very complex. What do you want to run on these things in the first place? So this is the menu I brought, what I was thinking people would want to run these days when they run internet-facing services for others. LAMP stacks are pretty popular, I guess. Anyone using one? Something similar? I mean, the general category, not exactly Linux, Apache, MySQL, PHP. Sure, right? Happens every day. Everybody has one. You have a website, you have something like that. Or you run a mean stack, probably not quite as much, but there are more and more things happening in JS that get more and more complex. A lot of people also like to use React or whatever and replace some of these pieces with others, but the principle stays the same. You have these servers that are long-running services that start and should never go down, and that you want to upgrade while they're in flight. You want to scale them horizontally and shrink them depending on how much demand there is. And then you have these other things that run mostly as batch jobs, where you try to find out what happened over the day, probably run those at night, and then you fill your databases with things from both of them. Then you want to do some data mining on that, and so on. So these are typical things, right? Have I forgotten anything? Suggestions? Okay. So I'm thinking with, we call them frameworks with services or service infrastructure pieces like these. You can go a long way. And we have here search, Elasticsearch. We have some database stuff. We have Jenkins for sure. If you're in development and continuous integration, you use that. We use that. We can run Jenkins on Mesos, and we can run Mesos on Jenkins. So that's fun. And Spark and Storm, Torque, whatever. And you may even decide to run to host your own private services, and this is just one of the possible solutions there. Okay, what I wanted to list here were things that are 99% sure open source, so you can put your business together without actually buying too much, and you can be sure that you have an insight in how things run and so on, and all the other advantages you get. Now let's put this in reverse. So you're up and running and you're happy, and how do you want to actually install these things and set them up and run them? I said eventually we want to end up with the data center looking like this. So turning this on its head, what if this thing looked like a data center? What would it look like? Or one of these in a former incarnation. So you would start a program, say inter IE, whatever that is, and you would then be asked, which CPU would you like to run this on, sir? Or like way back when, anybody used things like Mac OS 6? I don't know, that's maybe most of the audience is too young for that. So you would be asked, how much is the minimum of memory you want to give this app, and how much is the maximum? And I remember faintly that DOS and Windows had similar things, and other OSs. You don't want to do that, right? Not if you're in a computer these days. You just double click and the thing starts up. And why do we go through this pain in a data center where we set up lists of nodes that participate in an application, where we set up port numbers where they connect to each other, and then if that fails, we set up complicated routines to find them again, where we tell the developers, if you open a socket connection, make sure you have a strategy when it fails to regain control of that connection. Look at and we have different strategies for that. We have timeouts all over the place, right? So that's a lot like this. And I'm not saying it's going to go away. I'm just saying we can make it better. Another problem that we have is we have a lot of static partitioning, which I said earlier is that you have these dedicated clusters that you know what they're doing, you know that they're not failing in what they're doing. So for example, you run a big data cluster that runs a lot of parallel MapReduce jobs. And you know approximately that your database and your data influx are this and that size. You have so many customers. On average, they produce this many data. So you need to run, say, 15,600 jobs on average, maybe sometimes 20,000, sometimes 13,000. And then you size your cluster according to that. And then if that changes, you go into budget discussions with your bosses, your IT administrators, and everybody. And that happens again and again. And because of the static partitioning, you have to do this not just for one cluster, but for several. So the general idea, grossly simplified, I have to apologize for that, is that you may sometimes have workloads that are complementary to each other. Like, for example, you're running a business with a customer facing web service that at least in some geos will have this shape where during the day people buy, in the morning they sleep, in the evening they sleep, right? And then at night you analyze what they're doing with your Hadoop jobs, and you have some memcache stuff that runs during the day or whatever for your analysts hacking away. And if you put this together, these shapes here would fit into one cluster, but if you keep them separate so that you can scale, then you may be wasting a lot of machines. Not everybody is very interested in this aspect. I'm getting to that, but some people aren't. If they are, they're really interested. And there are two sides to this. We know people who have a similar problem, but slightly different. They have a fixed amount of servers. And they know how many they're going to have, and it's going to be stable for, say, half a year to a year. And all that matters is how much they can do. It's not how much it costs. So it's important then to drive resource utilization rates up so that they get more queries served, for example, with a given hardware. So you can see this two ways. Or you can say, what's the least amount of hardware I need to run my business? Okay, so the proposed solution is, instead of hardware clustering, didn't leave that one as a mystery here, we're going to do software clustering. That's been around for a while. So we put a layer between the OSs, and here I mean Linux variants for single nodes, and those application frameworks. And this layer is supposed to provide us scale, multi-tenancy, and high availability, fault tolerance, all the good stuff. So now that we talked about the stuff we want to run, we need to talk about the stuff that enables us to run all that. And that also comes from open source. So the core thing that I want to spend some time on, significant amount of time on, is Apache Mesos. It's the, as far as I know, only full two-level scheduler in open source that I'm aware of right now. Maybe there are others. Please educate me if you know some. I know some 1.5 level, one-level schedulers, but none of them work exactly this way. Yes? Yes, I will. That's on the subsequent slides, but that's the key question, exactly. And then we have some meta frameworks. Those are frameworks. A framework is something that works with a scheduler as an application and runs tasks. And I'll get to that. And then there are frameworks that run other frameworks, or services that run other services. Think of it like the init daemon in your OS, for example. You could say that's an application of the OS, but really it's a service that enables your OS that happens to run on it and runs other things. You need something like that also, and we have that. Marathon is an example of that. Or you need something that runs cron jobs for you, and so we have that. Aurora and Kronos can do that. And Kubernetes does a lot of similar things, and so does Swarm. Kubernetes aggregates applications nicely into pods, and you may have heard a talk about this at this conference, so that's really cool. And another problem you need to solve is service discovery. So when you have multiple tasks running, how do they find and re-find each other? And there are some open source solutions to that. Console, HA proxy, Mesos DNS, and they all work differently. And everybody and his buddy have a different solution for that, and everybody uses a different one. We don't have the solution yet. That's a vexing point, and we're working on it. And you also need, for failover scenarios, some leader election stuff and some persistent key value store, and Zookeeper and etcd come to mind there. As something else, if you're an application developer and you view it from that point of view, you don't want to reinvent the wheel and build your own storage format and bring your storage system to your servers. So it's often the case that you have a flat storage scenario with something pre-installed. Okay. You use Linux, obviously, and then let's get to your question. So among these components, the key component is the scheduler. Two-level scheduling is following this principle here, that the application-specific functions should be in the hand of the application. A monolithic scheduler will get a vague description, more or less vague, sometimes quite accurate, but not in general quite accurate, description of what the application wants. In a two-level scheduler, the application contains written program that spells out what in what situation it wants. And I'm going to have a graphic how that works with Mesos. So the scheduler asks the application, here are some resources, what do you want to do with them? And there can be a Turing complete program making these decisions instead of just a matching of some attributes. And I think that's a requirement for general multi-tenancy. You get some multi-tenancy, but not the complete general case solved if you don't go that extreme. Okay, so here's how Mesos works as an example of this, as an instance of that. You have the application there that, let's say that's your Hadoop application that collects your customer data and boils them down to who's buying the most shoes. Okay, something like that. And the framework is then Hadoop or Spark or something else. And you use an adapted version that has a little piece of software in it that issues the task commands. And that one will listen to the Mesos master. The Mesos master beforehand has listened to the Mesos slave. The slave is think of it as a node control daemon, analyzes what it's running on and reports to the master, which you can think of as the cluster control daemon. Here's what I got. The master collects this from each slave, could be 1,000 slaves, makes a list, also knows all the applications that run against it, matches them up in an algorithm, finds out who's the most hungry, the most starving app, and gives them some resource offers. And then the apps, and this is the two-level part of it, decide whether to take these offers, reject them, or take them partially and launch tasks against these available resources. Okay, so it's a give and take. And what we're solving here is a really hard problem. It's the knapsack or bin pack problem. And you have in monolithic algorithms, they use a kind of a heuristic to solve it. And this uses an emergent behavior. So that tends to work a little better on average. And of course, a master can die. So if that guy dies, then you can get a new one and you have some on standby. And same for slaves, you can do a lot of that. And the framework needs to provide two parts. The scheduler is one, the executor is the other. That's you could say, a task supervision daemon. Something that the slave starts before it starts the task, and that then decides how to run the task and finds out whether it's still running, whether it's lost or killed or something, and reports that back to the framework indirectly through the master. And this is how you keep tally of what your tasks are doing. You know when they're gone, you know when they're successful. And so in the framework, you have to program something that basically does all the bookkeeping for that. And so it's cooperative. You can think of that as, a kind of cooperative behavior, as in cooperative multitasking. A lot can go wrong, but if everybody does it right, you have a very balanced view of the world. Now, not everybody needs to implement a scheduler, though. You can run your application in different ways. You can run a vanilla job, and if you want to do that, so you have a monolithic app, maybe I have an echo hello world lying somewhere, and it's really important to me, I just want to run that. Or something similar that has input, run this, output. And I don't want to modify it, I don't want to build a framework out of it, it just needs to run at 1602 today. And only if maybe the other app has produced the output. You can program all this in a meta framework that Kronos, for example, that provides all the scheduling in it and then just uses Linux to run that task and observe it. Okay, and reports back to Mesos. So you can wrap pre-existing legacy apps that are not too complex in distribution that way. The second step is, well, you do write your own software, and I'm going to show you how to play with Mesos. That will be on subsequent slides. I'm going to give you a gist of that. That's not the regular case. You can do that, but typically someone will do that for you, and then there will be a large amount of additional application logic that's kind of prefabricated, and then you build your app on top of that. Hadoop would be an example, Spark would be an example. You wouldn't rebuild Spark for your one analytics app. Okay, you would use it, it would already come with Mesos, and then you would build your app on top of that. And this way we finally end up with something that resembles more or less an OS with services, then is more than something that is just a kernel and then you write raw apps against that. Third way is you have services that are a lot like the vanilla jobs, but they come in a special group format. For example, web servers. You want to scale them out horizontally and they're all the same. And they need to know where the load balancer is. So that's a little bit more sophisticated than the pure vanilla app. And then you use what we call a meta framework. It's a framework that speaks to Mesos on behalf of these. It knows how to make new ones, how to upgrade them in a rolling way, knows a little bit about the composition. Kubernetes knows a lot about the composition of the general app from these small ones. And somehow for these apps you solve the service discovery problem. Several options. You can play a lot with Kubernetes, Docker, Mesos DNS, things like that. There's always an option for you depending on what you're doing. And the fourth option is, well, you program your own. And I'm going to show you a little bit how that works. So for that, you use the Mesos Framework API. And that's a protobuf messages over HTTP is really what's underneath it. And what we've built is a lot of, well, we as in the Apache Mesos open source project in this sense, is a lot of protobuf messages over HTTP wrapped in interfaces in different languages. Pretty much every language that you can generate protobuf source code for. So starting with C++, there's Java, there's JavaScript, there's Python, there's Go, a lot of these. And soon there will be a pure HTTP JSON interface, then that will make it even easier to connect to Mesos. But right now it's already available in like a dozen languages. Okay, what's it look like? Well, you need to implement these two pieces I talked about. One half of two-level scheduling. There's the master, and you provide this thing that responds to offers. You need to be able to say something when you receive an offer. And you need to be aware of what happens to your tasks after you started them. That's the minimum. Now there are a bunch of other callbacks that I'm going to show, but they're not as important as these two. Additionally, you can build an executor interface implementation, and that is for monitoring individual tasks, finding out how they're doing. You can use WaitPit in Linux a lot for that, for example, and that's exactly what the command line executor does. That comes included. It basically runs a shell script, does a WaitPit on it, and reports what the outcome is. So that's the simplest executor. You can build your own, though. For example, you could make one that injects a jar file into a running JVM, starts something in a new application class loader without starting a new process, and then has a socket to it, and then reports how this thing is doing. You can go arbitrarily fancy with an executor. It's totally free form. Or you can use the pre-formatted ones. Another really important one that comes included is Docker execution. That's something where you specify a Docker image or a Docker file. It gets pulled down, cached, instantiated, and a Docker command gets run. And that's really a crucial one, because containerization is key at that scale. Okay, what does the SPI? Well, the API is actually an SPI. That's how I see it. You, the framework, implement this service interface, and then you're a framework, service provider interface. And these are all the callbacks. The first two ones are about registering with the master. Then there's the all-important resource offers, and it has two parameters. The first one is like a remote control for the whole cluster. The scheduler driver is a weird name. Just think of it, this is my remote control. I want to switch on something over there, run a task, driver.do that. I want to kill this slave over there, driver.do that. Something like that, okay? So you got power in your hands with this instance of a class that's connected to the master and can talk to it. And the rest is information for you, what kind of resources are available on what hosts. That's what offers is. So how many CPUs, how much memory, what storage, what bandwidth, those kinds of things. And if you see such an aggregate of resources, then you react and say, I want it, I want half of it, I want a quarter of it, I don't want it. Once you have it, you then issue a command, and I'm going to get to that in the next slide. Here's an example. So I used Java for this because I hope everybody speaks Java, or I could have used some other language. Maybe Python would have been nicer. I don't know. Anybody doesn't speak Java? Nah? Okay. I don't explain what the task generator does. That's your own internal, let's say, database of things you want to do. Hash table or whatever, or just a list. Something that you can take from, or it could be a FIFO queue with some editing in it. You can organize that or you make the tasks up on the fly. But as long as you have tasks, you keep going. If you're done creating tasks, you find out eventually, well, I had 1,000 things to do, they're all done. Then you start declining offers. That means you say, I don't want this offer anymore. And what happens? The master takes the offer, gives it to another slave. Okay? So you're basically done then. And when you get your last status update, that the last task is done, then you can stop the driver, which means this framework goes home, it's done, it is no longer connected to the cluster. And yeah, and once you have an offer and you find it interesting enough, in this case you find all offers interesting, but you could filter them. I haven't put that in there because of the slide size. You generate task infos for the offer. Task infos are descriptions. I want to run on this host name that you sent, and here's the shell command, and here is a URI where I can download some software that needs to be installed there, or here's the Docker image, and so on and so forth. Very, very flexible to organize that, but essentially this program line there then will get your tasks running. And the next thing you know, you get status updates. So you sit there as the framework, a protobuf comes flying by, goes into the event loop, this callback happens, status update. And that's how you find out what happened to the tasks. They have an ID, and that's how you match what you started to what happened to them. That's it. So from the developer's perspective, aside from this piece that I showed, you focus on the application logic, and you do not think about the data center structure, because that's all in Mesos. You care about what to run, Mesos cares about where to run. That's labor division, good old principle. And you avoid network-related code, except if your tasks communicate with each other, then of course they contain some. But just to get them out there somewhere and report back, you don't really need any network code. You can send so-called framework messages that will go through Mesos, and it will know how to route back. You reuse the built-in fault tolerance and high availability. You reuse infrastructure frameworks. Also, for example, you could first start HDFS as a Mesos framework, as a genuine framework, and poof, you have storage everywhere. And then your app can just use that storage. Or you could say, I want DNS, you run Mesos DNS, poof, you have DNS that knows the names of your tasks as host names and can reconnect those to IP addresses if they migrate. Things like that. So that's what I would call an infrastructure framework that is kind of part of the ensemble that I would describe as an OS in this context, above the Linux OS that runs a single node. And in total, as a developer, what you really want then is an API and also an SDK. So that's under construction. From the operations engineer's perspective, that's all hunky-dory, but what you really care about is how easy is it actually to manage my data center, to run my cluster, and how uniform it is. We hear this all the time. Oh, we are a company, I talk to a company that's growing like, yeah, double-digit percentages per year, buying other companies, and they buy like on average 15 companies a year, and guess what? They all have a different way of running their clusters. It's hardly ever the same. So they want that they can run across the company clusters the same way, and they need to agree to one way, and they want to train people once, and they want them interchangeable between different divisions of the company, and so on and so forth. So uniformity is pretty much key. Or you can't really scale your business, or you have a lot of islands, and then you're smarter than me in how to manage that, for sure. Probably for other reasons also. And hardware utilization rate is something that is also often managed, but not necessarily always top of the list. What's also very important, I mentioned that in the beginning, you want to scale up as the business grows, and you want to scale out sometimes. and so on. It's all about cost and time. And what I'm not going to address a lot today, I'm afraid, is monitoring and troubleshooting, but I heard there are some really great other talks in this conference about that, so I'm going to leave that out a little bit. Okay, so once you have all that, you basically, with a two-level scheduler and all these frameworks, you're in good enough shape. And that is kind of where we were 2 years ago, and then this whole thing took off, and more companies are now using open source Apache Mesos, okay? It went from like 4 to thousands. But there's still a lot of work to do. We're not done here yet. This is still early days, and we're still building it as we're using it. And a lot of these features that I'm talking about here have just come into fruition or are still under development and getting some touch-ups. Whoops, I was here. So to have true multi-tenancy, containerization is important. Okay, so Docker is integrated, can be integrated better. We always need to make sure that works really well, but there are also other container systems. What about those? Have to think about that. There's resource isolation. Not all the resources are isolated in the same way as equally well. And then there are more and more resources. For example, what about sharing GPUs? Anybody have a clue how to do that? Or isolate them so only one task can have them and the other actually knows it's occupied, right? Little things like that come up all the time. Resource and task attributes. I know that Docker Swarm, for example, has a relatively rich language to describe this from both ends, okay? And but it's not fully programmable. But the question is, how far do you need to go? And what's enough? Maybe it's great the way it is, and maybe you need to go a little bit further and need some extra attributes. Static and dynamic resource reservations, that's a really important one. Suppose somebody wants to run a big Spark job with 100,000 tasks, and you have a cluster, and now you have a second Spark job. Maybe this one is analyzing some genetic material or something, and you're running on gene 21. And the next one wants to analyze gene 22. Can you run them at the same time? How do you know? Right? Well, you could try, and what happens is the first one occupies the cluster, the second one runs at trickle speed, or it totally chokes. So what you can do is you could make some static reservation and say, among these 1,000 nodes, give me at least 100. And if I don't get them, I don't start. And this is a lot like OSs in the past for one computer where you said minimum memory, maximum memory. Remember that? So you can play this game now for all kinds of resources in a cluster. And then you get the same effect. You can double-click your application. It will say insufficient resources, : here is what you don't have. Or you can run two of them, and they both say, I want 100 CPUs, and then there are 100 extra CPUs. How do you make sure each of those gets 50, right? And what does it mean if one of them already has 300 and I want my 100 and there's only 300? You need to be able to cancel tasks and replace them with new ones. But maybe nobody has programmed, hey, you can't take away that task, then my application logic is broken. So we need some sort of cooperation from frameworks to make that happen. You cannot have zero information about the frameworks. So the frameworks that say nothing to the OS get punished and kept in confinement of not too many resources. And the ones that generously provide information, hey, I need this at a minimum, but I'll take everything you got if you give me. And in some specific terms, they get allowed more resources as available. Okay, so they benefit from restraint. Reservation levels. Oh, I forgot what I meant by that. Oh, that was exactly what I just talked about. You say what kind of certainty you want for getting these resources. Okay, you need meta frameworks because otherwise you will not have all the applications that are possible and thinkable on board. Some of them are just too hard to change, or why change them if something else can run them cheaply? And you also want to update the system, the apps, the frameworks. Everything needs to be dynamically upgradable. You don't want to shut down your data center, install something from scratch and so on. You know that. Okay, I'm not going to talk a lot about security. Any questions so far? Getting close. Okay. There are other features that are not quite as necessary, or you could argue are they also necessary. There's one other great scheduler. It's from Google. It's called Omega. There are some recent publications on that. And comparisons with Mesos, it's quite similar, but it has a few differences. And one of the biggest differences is it does optimistic offers. So in Mesos, an offer only ever gets sent to one framework, and it has the first right of refusal for those offers. And if it can sit on them for a while and hog them. With optimistic offers, you send the same offer to multiple frameworks. They could, in theory, simultaneously grab them, and then can sort it out later with a conflict algorithm who actually gets it, and the other gets revoked the offer again and gets balanced out. Optimistic because typically, if you send the offers out in a relatively widespread pattern, that doesn't happen too often, and you're fine. Only when there's crunch, then you can still switch off optimistic offers, and the mitigation techniques are, as described there, not so severe. So the goal here is just to have more throughput, okay, and better utilization rate and less spinning. Okay, oversubscription is another thing. Your tasks may be describing what kind of resources they need, but they may be lying. Your programmers who program the frameworks may make mistakes, or people aren't just that great at estimating, and neither is software. So this is not always an exact science. You say, I need this much memory, maybe you don't. Maybe you say, I want 4 gigs reserved for this task, but then it only uses 3. So you do the same thing as airline carriers. They book more tickets than they have passengers, than they have seats. They book more passengers. Not everybody shows up. We can do this here also. And then correct it when it goes wrong by resizing tasks that are not so critical, prioritizing which ones are more deserving of resources than others, and so on. Play all these games. Rate limiting. What do you do when your cluster is really, really full? And that feature is already in. Well, you could let it thrash, ultimately to the point where you have the TLB acting, and everything goes really slow. Or you could just limit at the master how many tasks get issued per second, and just turn that big knob, and then the activity quiets down a little bit. All the frameworks run slower because the task rates aren't as high, but you don't get the thrashing on the nodes. Okay, so you need mitigation techniques built in. And then ultimately, my favorite, auto-scaling into the hybrids cloud. You own some of the hardware, and you rent what you need extra on a as-needed basis. Okay, but long topic, not getting into this now. Infrastructure frameworks and so on. One of these, remember 2 slides back, I said task containerization is Docker. Here's how the Docker integration works in like 8 simple steps. What happens when a task gets launched, but I want to get through the slides and allow you some questions, so I'm going to cut that a little short. Essentially what happens is the Dockers get drawn directly from the Docker registry, which is driven by the number 3 arrow, where the description comes down to the slave, and the executor then knows how to run a Docker that comes from there. And it's built in that the Dockers run in an LXC, and then you have lots and lots of little Docker tasks orchestrated in places where you never knew before where they would land in the cluster. Other schedulers that also run on a 2-level scheduler, Yarn, Kubernetes, and we're working on Swarm, but not there yet. It's kind of new. You can basically build multiple Yarn clusters inside a Mesos cluster. Or you could build multiple Kubernetes clusters inside a Mesos cluster, virtual clusters, so to speak. And that's one way of looking at it. Another way of looking at it is, these are just meta schedulers, or meta frameworks that are a little richer in structure than the ordinary pretty flat meta frameworks like Kronos, for example, or they're even richer than, in some respects, than Marathon, which mostly is for horizontal scaling. Can do a few other tricks, but that's its main game. And so Myriad is for big map reduce things, for example, is really great. So if you want to make really, really sure You can exchange that with static reservations a little bit. There are always multiple ways of doing things. I would say if static reservations works great, maybe you don't need this, but maybe it's never going to be that great. There's a lot of discussion going on. But if you want to make for sure today, you can do this and build a yarn cluster inside a Mesos cluster by requesting resources for these yarn endnodes that execute the tasks C1 and C2. You can have multiple of those and have these resources all reserved and then schedule among them. Okay. Node managers. That's what I call them. And likewise, this is already a slightly older project. It's coming into fruition now. And yeah, I can't talk about it too much, but I want to show you roughly. Just look at the colors. The red stuff is the genuine Kubernetes software, and the green stuff is the Mesos software, and the this color here, lavender or something, that is where the tasks run. And you can the important outcome is you can co-inhabit Kubernetes tasks, long-running services with batch jobs in the same cluster. And the rest is just how you orchestrate that, how you replicate, what kind of container arrangements you have with pods, and so on and so forth. So somebody's thinking about that. Okay, the end result of this is that you get more portability than I would claim in any other way. But there are so many ways to skin that cat, so don't take my word for it, try it. But that's the general overview. You can be in the public cloud, you can be in your own managed cloud, helped by somebody, or you can be on your own data center. You have this abstraction layer, and every problem in computer science is solved by abstraction, by one level of interaction, right? And on top of that, you have your meta frameworks to help you run apps. You have your infrastructure frameworks to shape them. You can run your own frameworks, but you can also run some vanilla apps. And hopefully, that solves in the 90-10 rule almost all the cases that matter. And then maybe there are some strange cases where it's a little bit difficult to adjust and it takes some extra effort, but it should be rare. And for most of your stuff, you should be quite portable. And that gives you the user perspective you run everything you need, hopefully, and you have return on investment and safety of investment, hopefully. And you really focus on running your apps and not so much on what your data center looks like. So I claim the data center is the new form factor if we get all this off the ground. And as a developer, it looks like it. As a user, it looks like it. And as an operator, hopefully increasingly also. So not quite as much. There will be always be some operators. So, but hopefully it will get easier, more uniform. And these are the main ingredients in the talk that we went over. The importance of the two-level scheduler, which I think is the necessity to get to a really single production cluster. We talked about scalability and portability. And containerization, we should have a separate talk about that alone. It's all about automation. And that's it, I think. So that was from a very high-level perspective, and that's why we have 5 minutes of question.
What about if you're running tasks that live for a very long time?
Yeah.
Right, so days or weeks, and very kind of different usage profiles. So I guess what you're saying is you could either have a static thing where you just say, block out this much resource and never let it use more, or you can do something dynamic and then you have to deal with all this conflict stuff. And does Mesos support all of that, or?
Not quite yet, but in the next few months, yeah, we should have all of that. Right now, if you have a task, what it will do, it will use the resources, not give them back. Yeah. So if it doesn't stop, then it still has the resources.
It just has
Yeah.
block, whatever.
Yeah, you just use that machine until it falls over.
And Mesos will ensure that there's always enough memory available or CPU.
Well, Mesos knows how much memory there was in the first place. You dedicated that memory to this task. If the task uses more and then falls over, that's not Mesos' fault.
Okay, but the app would fall over and Mesos
Yeah, the app would fall over, and Mesos would take notice. There would be a task failed status report going to the slave, which would then to the executor, or the executor would find out the task failed, would tell the slave this failed. The master will tell the framework. You and your framework will have programmed, maybe in Marathon, for example, that's a typical case where you run your web server. Oh, my web server fell over because this CGI command used more memory than I had configured it for. I don't know. Or no, CGI would be a bad example because that's a different process, but something else. Web server falls over, and you notice, and then guess what the meta framework does? It knows the template, how to run the thing. It knows how to connect it to the load balancer and to the other web servers, and we'll just start another one. But it may not be on the same node. Hmm? Yes. Yeah, I don't know the current status of console. You refer to console not just for the service discovery problem here, but for the other. Yeah, so I can tell you where Mesos is headed, that you don't need either. We have our own replicated log inside Mesos already, and we want to dedicate that also to the purpose of master leader election. And once we have that, we don't need either Zookeeper or etcd. Marathon is just going to use the Mesos itself then for that purpose. Hmm? That's coming up in a few months, or maybe is already almost done. I have to check. Yeah. Who's using Mesos already? Not so many. Who's heard of?
It's not in production yet, but we're trying.
Yeah. Just one more question, then it's you. How many of you have heard about it before this talk? Okay, that's wonderful. Last year that was a lot less. Okay, you're on. Yeah, let me go back to that slide. So there were these 4 ways to run things, and the number 4 is the exception that you have to build your own framework. And if you do, we help. And we don't usually charge. And there are other people in the Mesos community who do the same. We're just a big community who want to make stuff work. And there are a lot of other organizations, many of them companies, who have frameworks or who back frameworks. So we try to help Mesos along as much as we can, and there's also Twitter helping Mesos along as much as they can, and other companies who do the same in a community. And there are community efforts behind each one of these things here. Where are they? These ones. So there is a big ecosystem coming into existence with all the frameworks that you hopefully that you need. And then it should not be too frequent, or it shouldn't be the common case that most of the frameworks, or maybe even just one that you need, you have to program yourself. Now that said, if you come into the situation where you still have to program your own framework, it's not really hard. We run hack weeks with some people who are interested in that sometimes in the US, unfortunately, at the moment. Within days, people get their frameworks up and running, typically. Now, it can sometimes take longer. Now, there are complicated engagements. For example, Kubernetes is a little complicated. You wouldn't get that up and running in 2 days, and then you have to work a little bit harder on that. But it also does a lot that has to do with the system, rather than just being an app. So the more involved in the system itself it is, the more complicated it gets, the more it's just at the app level, the easier it is. I wrote a little framework myself in a couple of days. And the weirdest thing runs on Mesos. Take, for example, the MPI framework. That's also something I wanted to point out. It doesn't run any damn better on Mesos than it would without. That's not what this is about. That's also an important point I wanted to make. You get the same performance, the same startup speed pretty much, No benefit whatsoever respected compared to running it outside Mesos. But guess what else you get? You can run MPI and other stuff on the same cluster, and there will be an overall resource management, and you don't need to have your separate MPI cluster anymore. That's really what it's about. But the framework itself, it's really tiny. Basically, it just starts these MPI nodes. There are two versions of doing it. These M something, forgot the name nodes, and then there's some daemons that need to be started. And when they're all up and running, then you can start your job. And these two phases, you can program that in hours. Just to give an example. Also, Spark and Hadoop are relatively simple. Jenkins is relatively simple. You just scale out. Yeah, but everything is a little different. So that's why we think there isn't a one-size-fits-all, and there isn't even a description language that's good enough. But you want all flexibility, and that's why this is programmable. Yep.
So is this part of the, I guess, you mentioned the data center operation? Like maybe 2 years ago it was Mesos, but now it's data center operation. Is that where all this comes into play?
Yeah, think of it as a distribution of useful things that right now aren't maybe as rich as you're used to from Linux distributions when it comes to single computers. It's nowhere near that. But if you think at very early Linux, then it's kind of closer to that. Not even that much, but there's much more to come. But that's clearly headed in that direction, that you get a more complete picture of what you... I had another slide, what you want from an OS. Should all be in there. No, no longer there. Sorry about that. But essentially, you want an API, an SDK. You want system daemons that run stuff for you in an easy way. And you want security. You want some user management. You want a GUI. You want a CLI. So one thing I didn't mention is we have, for example, a command line interpreter that lets you say, whoa, wherever this task is running, I want to SSH into that box and read the log or manipulate that box or whatever. I didn't talk about logging. That comes with it also. You want to hook this up to, say, Splunk or something like that. Or all these things need to be, all these struts need to be made and connected. And then we have something that amounts to the look and feel and usefulness of an operating system on top of a data center. And I don't say cluster here, only for the reason that we only really need one production cluster once we achieve that. And that is your data center then. Yeah, that would be another layer, as I understand it. Now, there are some companies that kind of conflate these two layers. I know that there's a system from Facebook, Tupperware, that does a lot of that. I know that Microsoft has something called Autopilot. I'm not sure, I'm guessing, that addresses both aspects. We're trying to do one thing right and then go from there. Yes, and it's not just Mesosphere, it's the whole ecosystem here. And of course, at the center of that is the Apache Mesos open source project. Yeah, we're just part of the community there.
So I think we are done.
Yep. Thank you very much, everybody.